This tutorial will demonstrate how you can start automating recognition of critical machine conditions in your production processes, the goal being to minimize downtime and maintenance costs. Although our algorithms can be extended to deal with any kind of sensor data, in this presentation we use acoustic emissions only for diagnosing machine conditions. In order to set up a project, we first have to check what would be worthwhile targets for recognizing machine conditions automatically, especially kinds of defect. Are we able to identify these conditions reliably? Can we generate the necessary measurement data that are indicative of risks and defects? If we have been able to identify critical conditions only manually or by consulting experts, automatic diagnosis should be rewarding. Under which circumstances is our approach applicable? First, we have to be able to classify machine conditions of interest at least manually or by experts. Secondly, the machine conditions we want to monitor have to be reproducible. There may be a list of conditions we want to diagnose automatically, for instance in different phases of a production process, or at different stages of a life cycle of a machine and its components. In this case, we may take a time-stamped series of sensor data snapshots for classification, or even for ultimately forecasting remaining useful service life. In this tutorial, for simplicity, we will only demonstrate the case of distinguishing between three conditions: good, bad and off. Of course, the procedures could be extended to more conditions. Our demo setup consists of two bearings powered by electrical motors. The original idea was to use two sensors. But actually, one sensor is already sufficient. The good bearing the bad bearing, both running approximately at the same constant speed with some fluctuations. The adhesive tape is to lock the sensor exactly in the middle and prevent it from slipping. As acoustic emissions data acquisition device, we use a Fallen-Fire Sonic capable of sample rates up to 10 MHz, of which we use only 2 MHz. Electricity supply and data transfer is via a PoE device connected to the Ethernet gateway. Starting now. All devices switched on and connected. Let's start teaching the machine learning classifier with condition bad. Starting the live trainer. OK. Starting the training monitor. Here we are. The machine learning trainer outputs an indicator that tells us how dissimilar the signal from the machine is to what the trainer has already learned. The dissimilarity index should eventually go to 0 in the course of time, and deviations from 0 should become more infrequent. If we arrive at a constant zero curve, we cannot improve by more training time. Our live training monitor shows us the percentage of zeros over training time so far, and the value for recent is the percentage during the second half of training time. So watch how the percentages displayed at the top are increasing. Since there is a warming up once the bearing is running, and because speed may fluctuate, we have to choose a training time that is sufficient to cover the acceptable variability during a specific condition. We have chosen a training time of 30 minutes. If in a production process a condition lasts only for 10 seconds, for example, then we would only train for 10 seconds. However, the condition must be reproducible, so we can repeat the training in order to capture all the admissible variability within this condition. Main parameters for training are the frequency range of the acoustic signal that the classifier will analyze. We have chosen a range up to 240 kHz. The time interval for FFT generation, it will be 0.01 seconds, which means 100 fast Fourier transforms will be generated per second. The machine learning trainer will create statistical profiles of machine conditions based on the FFTs. Okay, let's now teach condition good for 30 minutes. The dissimilarities decrease over time, and the percentages of zeros keep increasing. Our third condition for automatic recognition is when neither bearing is running, which is condition off. We are not showing this training run, which also took 30 minutes. Okay, now we have completed our training runs for condition good, bad and off. Next, let's do a condition monitor performance test after training runs of 30 minutes for each condition. The condition monitor dashboard is accessible with a web browser, both locally and over the internet. Bad bearing. Good. Bad. Good. The condition monitor seems already to be working. However, we have to evaluate condition monitor performance over longer time periods. Let's evaluate the accuracy of the machine learning classifier, first testing condition bad for 30 minutes. Starting the condition monitor. The condition monitor is running now. Starting the performance monitor, which is available with some time delay. Here we are, showing a flat line at -1. That is, classification is 100% bad, which means no error so far. Watch the statistics at the top. Classifier parameters. The frequencies specified define the frequency range the classifier will look at for analyzing the signal. A reaction time of 0.15 seconds means the classifier will look at 0.15 seconds of the signal for deriving a decision. The overall response time of the condition monitor is larger, depending on a smoothing window parameter and the update cycle of the web browser dashboard and data transmission delay via internet. Achieved condition monitor accuracy during 30 minutes is 100%. The classifier was error-free during 30 minutes. Next, let's evaluate the machine learning classifier accuracy, testing condition good for 30 minutes, after 30 minutes of training this condition. Starting the condition monitor. Starting the performance monitor, which is available after some time delay. The graph shows a constant line at +1, which means 100% condition good. Test result after 30 minutes, 99.98% accuracy, and for, let's say, 28 minutes, 100%. Can we expect that the classifier will perform equally well next day after our initial training? Unfortunately, the answer is no. Experience shows that performance tests immediately after training generally produce good results, while repeating performance tests some time later may produce much worse results. This may be explained by changes of environmental conditions from day to day, for instance, changed air temperature, humidity, exposure to heat radiation, lighting, convection, a draft or breeze in the room, or dust. And secondly, it may be explained by the variability of machine behavior during warm-up. The condition monitor history here is displayed by two graphs. The right-hand graph shows the classifier output oscillating between plus and -1, and according to statistics, the good bearing was recognized only for 88.93% of the second half of the testing time. The left-hand graph shows the history of percentages, and we see that the green dotted line for a recent good percentage begins to rise after approximately 15 minutes. This can be interpreted as the result of a hitherto unknown warming up behavior of the machine. While in industrial production environments, even air temperatures, humidities and other environmental conditions may be strictly controlled, this has not been the case in our test room. In fact, testing for reliability showed that our bearings, including the drive belts and electrical motors, kept changing behavior from day to day and also changed speeds during 30-minute tests. Since our goal has been to achieve near 100% condition monitor accuracy nevertheless, it was necessary to repeat cycles of condition training and performance testing a number of times. And this is shown in the following sequence of video clips. So the basic rules for the training and testing process are: alternate training and testing until performance is consistently high, also after longer pauses of machine operation. And choose good classifier parameters such as frequency, range and reaction time to optimize performance, as will be explained later. Here we show the additional training of condition good on subsequent days. So the total training time goes from 30 minutes to 60 to 90 to 120 minutes, and so on. The decision to go on with additional training was always based on intermediate test results, until tests revealed that classifier performance remained consistent near 100% for repeated machine cold starts. Now let's look at the history of training for condition bad, which results in a total training time of 300 minutes. Note that even after many minutes of training, surprising dissimilarities may be detected by the trainer due to changed behavior of the machine. In order to have better coverage of the warm-up phase, later training runs lasted only 10 minutes. We have finally arrived at concluding tests that demonstrate classifier performance is stable, near 100%, and reproducible with machine cold starts on subsequent days. It was decided that choosing a classifier reaction time of 0.2 seconds was safer for achieving consistent results, and in addition, choosing a frequency range of 100 to 240 kHz safeguards that the classifier will be immune against potential lower frequency interference. And this is the final result of a repeat performance test with the same classifier parameters conducted on another day. The outcome is similar, the accuracy near 100%, and results have been demonstrated to be reproducible. Mission accomplished. Summary. We have shown how to teach defined machine conditions with a live machine learning trainer, how to monitor training progress, how to use the real-time condition monitor and test classifier accuracy, and how to alternate training and testing and choose good machine learning classifier parameters until consistent and reliable high performance is achieved. The main advantages of our approach are: it offers an easy start into automating recognition of machine conditions, avoiding huge amounts of data to be stored due to real-time learning. Classifier accuracy can be evaluated in a live fashion, and high accuracy is achievable near 100%. And finally, the algorithms may work for many different applications.